All right. Get some PowerPoints up here. Instrumentation 4. All right. Calibration and configuration. Did both y'all do the trainer right here last semester?
No, I did the motor control circuit.
But you did this one. So you did some calibration and configuration on this one last semester. You will, and both you guys will whenever you're your 6 weeks and stuff like that. Obviously, for instrumentation, calibration is super, super important. I would say, like, whenever I was doing stuff like that, was just to come calibrate simple things like rail scales or any kind of scales, really. We'd have to calibrate. Trade terms, calibration is just making sure that something is, I don't have any trade terms highlighted, but it's the process of adjusting instruments so its signal, output signal or level of energy is representative of the non-adjustable input energy. So whatever you're putting in, it's the same thing as what's coming out. And you're just making sure that they're lining up. 5-point calibration, or I guess I can write it like this. So what's our most common instrumentation signal? What? 4 to 20, right? 4 milliamps to 20 milliamps, right? You remember what the range was for that control valve, PSI wise? 3 to 15. So 3 PSI to 15 PSI. So calibration is making sure that whenever I'm at 4 milliamps, I'm at 3 PSI. When I'm at 20 milliamps, I'm putting out 15 PSI and everything in between, right? So whenever you're at like 16, you're at whatever you're supposed to be, right? A lot of times, I get a little ahead of myself, but a lot of times you'll do, it's called a zero and span calibration, which is probably spanning, zeroing, yes. So they have a zero and span, which is your most basic type of calibration where you do the zeros, because this is 0, right? This is our 0, this is our 0 for our air, and then this is 100%, so this would be 0 and span. You also have 3-point calibration and 5-point calibration. So while I say 3 and 5, it's not 3, it is 3 different points, but you would do, so 3-point calibration would be 0%, 50%, 100%. But you don't just do 1, 2, 3. You have to. You actually go 1, 2, 3, 4, 5. You go all the way up and back down. But you have a 3-point calibration, and that's just more accurate than a 0 and a span because you're doing something in the middle, right? You also have a 5-point calibration. So 0 to 20s. 25, 50, 75, 100%. Same thing. I'm going 1, 2, 3, 4, 5, 6, 7, 8, 9. So whenever they say you're not just taking, you're not just doing 5 different ones, you're doing 9, but at 5 different points. Does that make sense? You're going all the way up and then back down. So that's your 0 and span, your 3-point calibration, 5-point, and that's in order of like least accurate to most accurate. Range and span, I think you'll probably do the highlights for those in the book, but those are good to know than most everything else I've talked about. My first full highlight is the first sentence on the page. All instruments that provide a proportional output signal based on the input signal or level of energy, must be accurately calibrated in order to function properly within the loop. Calibration defined, second paragraph, beginning of the paragraph all the way through the sentence that has the multifunction loop calibrator in it. Calibration involves proportionally matching the output signal or level energy to the input signal or level energy. This can be accomplished by using a loop calibration test equipment that provides a variable energy source to the instrument's input, while a second device reads the output signal using an appropriate meter. Calibration can also be done using a multifunction loop calibrator, which provides the energy source and measuring capabilities in a single unit. So I just got a multifunction loop calibrator. I'm making sure everything works on our trainers before I let you guys do it. But that is something you will mess with this semester. But essentially what I just said is just talking about that. Making sure your zeros match up, your 25% and everything matches up. That's calibration. Last paragraph on the page is everything is highlighted. Even going into the next page, the whole paragraph's highlighted. Instruments used for calibration must themselves be calibrated in reference to an accepted standard. In most cases, for calibration to be valid, the instruments must be traceable to a national standards body such as the National Institute of Standards and Technology. Normally, instruments are sent away to calibration lab on a scheduled basis. Calibration sticker on the instrument and matching certificate confirm the calibration and traceability status and shows the date of calibration. Calibrations then performed using that instruments are deemed to be both valid and traceable. If any of y'all seen like I don't know if I said it in the last class, but like the most accurate cube that weighs, what is that?
It's 1 kilo or something, like the French.
The kilo, yeah.
Like
Yeah.
having like this encased glass thing and yeah.
Not that.
Yep, that's the one encased in the glass with glass.
So this is like obviously not for
Calibrating.
well, it is.
Is it?
Everything, but not us, because this is metric.
Right.
So metric, most of the world, everything is traced back to this. Like this is the most accurate kilogram in the world. Like you can't, obviously, like you can't touch it, anything. Stuff like that. And we actually have, there's a new one, not a new one, but there's one in the United States that everything's traced back to. But that's all it's talking about. Like everything has to go back to like a known source. And even if you look in like your regular multimeters and stuff like that, and you pop the battery off the back, usually like my fluke meter says like get calibrated every year. My meter, wherever it is, because I lost it, is 10 years old. I've never had it calibrated. It's fine for what I do. But if you guys end up doing something like super specific or anything that has like nuclear radiation or something like that, especially nuclear, everything radiation wise has to be traceable back to a standard and stuff like that. So just watch that stuff and make sure that you're getting stuff calibrated back to like a set standard. 111, input signals or energies. First sentence is highlighted. Instruments that are in direct contact with the process are designed and manufactured to operate within a specified process input energy range. So that's like the lab equipment that's out there, like the control valve is made to operate within 3 to 15 psi or something like that, or a valve is made to operate up to 100 psi. Like everything has a range that it can operate in, and if you go outside that range, then it's not going to be a calibrated setting. Like it's kind of an unknown because it was never calibrated at that level, and it can also damage the equipment. 112. These are what some calibration stickers can look like, but yeah, sometimes whenever you calibrate stuff, your company will have its own set of documents that you have to like submit and put on file and whatnot. 112, output signals or energies. First sentence of that is highlighted. Output signals or energies from instrument are proportional to the input signals and represented accurately. So that's just what I was saying on the board, like 4 milliamps would represent 3 psi, 20 milliamps would represent 15 psi, and so on and so forth. Calibration concepts 113, second paragraph is highlighted. An instrument's range consists of its lower and upper input or output limits. For example, if an instrument can measure a process value between 60 inches of water and 400 inches of water, its range is 60 to 400 inches of water. Similarly, if an instrument can output a pressure between 3 and 15 psi, its range is 3 to 15 psi. Fascinating stuff, right? They're going to have a couple questions on figuring out what that is. On page 3, the second and third paragraph go through like how to figure out what the span and the range is. I'm going to read through these 2 paragraphs just so you have an idea, but you're going to have a couple questions where you have to figure out what the range and what the span is. And it is confusing. People do get confused by these, so make sure when you're going through these questions you have an accurate separation of definition between range and span. So when the minimum zero value for range is a number other than 0, an additional step is required. For example, if an instrument has a range of 60 to 400 inches of water, the 50% point of the span is not 170 inches of water because the zero value, the minimum value of the range is 60 and not 0 inches. In this case, add the calculated 50% span point to the zero value to determine a true 50% point. So 170 plus 60 equals 230. So 230 would be the 50% point of that span. Another example is the same instrument has an output range of 3 to 15 psi. It has a span of 12 psi. 15 minus 3 is 12. But since the 0 point is 3 and not 0, a 50% output will be 9 psi. 12 times 50% is 6 plus 3 is 9. So 9 would be 50%. Does that make sense? Or is that too confusing?
It's doing it weird.
So it's doing it kind of weird, but say I had...
Like I would just subtract the difference between both of them and divide that by 2 and that would be the middle one, right?
15...
Like if you got 15,
No.
3 to 15,
3, so if you did that, you
the
said
difference
50,
is 12. So
and divide by
6
2 is 6,
plus 3 is 9.
plus 3, yeah, which is what they're doing.
Oh, that's what they're doing?
So that's what they're doing. So like to find my 50% point, you gotta take that minus that, which gives you 12, divide that by 2, which gives you 6, and then you have to add your 0 to that
Wait, what?
to get 9.
Okay, yeah. Yeah, I get it, yeah.
I'm not, yeah, that's, I feel like I'm making it more confusing than it should be. And I also should use the red. So if I had 4 to 20, what's my range?
4 to 20.
4 to 20. What's my span?
0. 4 to
16?
16. Right? This is my range.
Right. Span is...
My span is that minus that. So I have 16,
Oh,
16
yeah.
different points. So 16 is my span. And then if I wanted to find my 50% of 4 to 20, what's my math?
Subtract 4 from 20.
20 minus 4, which gives me 16.
You subtract and you add 4.
Divided by 2.
Divide by 2
Plus 4.
is 8. And then you have to add your 0, which would give you 12.
Right.
So that's your 50%.
Cool.
Right? Is everybody good with that? Calibration process 114. The whole second paragraph is highlighted, keying in on the first sentence. The first sentence is the most important, but the whole paragraph is highlighted. Second paragraph 114. One of the simplest forms of calibration is the zeroing and spanning of the instrument. That's what I said in the beginning. Zero and span is the most basic, but the most common. When you zero the instrument, you set its output value to its minimum range limit, which represents a zero input from the process. For example, consider a pneumatic transmitter. It's used with a process whose range is 20 to 150 inches of water. the zero value is 20 inches of water. If the transmitter's output range, is 3 to 15 psi, its zero value is 3 psi. At 20 inches of water, input to the transmitter should produce an output of 3 psi. If it doesn't, you must adjust the output until it does. You will literally, like Darren and Mark were doing this today on that lab. You will do this on the lab that's right there. Moving on to 120, 5-point calibration. I've got the first sentence highlighted, but this is what I talked about before. First sentence of 120. When performing a 5-point calibration on an instrument, the instrument's output is checked for accuracy and proportionally against the input signal that is 0%, 25%, 50%, 75%, 100%, 75, 50, 25, 0. In that order. Everybody good with that? Flipping over to page 4 and 5. We'll not be here today. Page 5, first full one-sentence paragraph is highlighted. A 3-point calibration is essentially the same except with fewer points: 0, 50, 100, 50, 0. That's the first full sentence on page 5. So they go through the steps on doing a 5-point calibration, which you can read through those if you want. I have the first half of step 9 highlighted, which is just figuring out your 50%. So step 9, I've got the first half of it highlighted. Calculate the expected output value. For example, the 50% point for a 4 to 20 milliamp output is 12 milliamps. 20 minus 4 times a half plus 4 equals 12, which is what we just did. Everybody go with that? So you should be able to find percent. They should be able to give you a range. You should be able to tell what the span is, and then what your different points are for a 3 and 5-point calibration. All right, I am just going to keep going. That's all I have for section 1. I want you to do section reviews as part of the homework. Okay. I'm not going to, like I normally would stop, I'm just going to keep on lecturing, and that way I can get y'all out a little bit earlier. You good with that?
Yes, sir.
Alright, section 2. Pneumatic and analog calibration. So you're going to have different types of instruments that can do this stuff. You'll have crystal gauges, a fluke gauge. They have that GE Druck that's will output a pressure with that little pump. Some of them have a pump built in. I think that that crystal gauge has a pump built into it. Maybe even the fluke one does too. You can see the button that says pump. But that will literally pump up a piece of instrumentation up to a certain, like if I had a valve that I had to calibrate to 3 to 15 psi, and I didn't have an air source, I could take a meter like that, or you can have, let me go grab it. So this is literally one of the pressure transducers that's going to go on that methanol plant in the back. So you got an input and an output. They've got them screwed off right now, but you can see like I can, I could unscrew that. This is called like a stinger. It's probably good for if you're getting into instrumentation. Like they're just two little fittings, and like I could take this off, and like this is what I would unscrew and put that in there, and then I can have I forgot the hoses in there. I have hoses that attach to like this, or the end of this. Like take these off and they can attach to this. And then like one side of this meter is my input, and I sit there and I pump it up to an exact pressure, and then I can read it on the other side of the gauge and make sure that it's reading correctly and outputting the right amount of stuff and stuff like that. Just know, like, $1,000. What? Stupid. $1,000. This is like the cheapo one. It's like $250. Very, very expensive calibration. I mean, this is work. Surprised this doesn't have a. This should have a
Calibration stand?
Huh?
The calibration stand?
No, I'm sure it has. Like that's probably what that is.
Right.
Well, this isn't have a calibration because this is just a pump.
It's a manual pump, yeah.
This was donated. It's like not for resale, so it's probably underneath that. But yeah, like you literally would go out to gauge, put your little stinger in, and then you can pump it up. If you don't have air supply, you can pump it up yourself and say I'm inputting 3, and then making sure that you're getting 4 milliamps on the other side or something like that. The trade terms. So we've talked about a dry leg. So you can use a differential pressure meter for doing level. So your dry leg would be, we've talked about this before. So if I had an enclosed tank, and I had my differential pressure meter right here, I have one side, this would be my high side connected to the bottom of the tank, because the more liquid I put in this tank, the more pressure that's put on the high side. And then I can have a low side. Sometimes the low side is just connected to atmosphere, and that's at 0. But if I don't, I can connect, if this is an enclosed tank, I can connect this to the top. And if I have, they have wet leg on there too. So I have wet leg and dry leg. So my dry leg is my dry leg would be if whatever's in this tank doesn't condensate or slosh around, anything, if whatever's in this tank doesn't get in this pipe, then I can leave it dry. If whatever's in here does condensation, like the temperature outside now, we're flipping 25 degrees outside and then it's 65 degrees today, like stuff is sweating today. And this would build up with condensation. Well, this is my 0, right? That's my 0 right there. So if I get a little bit of stuff in my 0 is not going to be right. And this isn't going to read the level of the tank right. So if that happens, they fill this whole leg with an inert fluid or something like that, and it's called a wet leg. And they fill it up, and then they set that side to 0. Does that make sense? So you can have a dry leg or a wet leg. You can also have a suppressed 0. So you messed with that last semester. Like, remember how you had to put in like negative 4.1 or 3.6? So literally on that trainer tank out there, you got a tank that's open atmosphere at the top, and you got like 10 inches, and you have a pressure transducer right here, right? This pressure transducer, it puts out a 4 to 20 milliamp signal based on how much fluid is pushing down on this. This has a little connection piece right here, so the actual like sensor is right here, right? And I'm measuring this as my 0 of the tank, because that's the bottom of the tank, right? So this is called a suppressed 0. So inside of that controller, you have to go put fudge. You have to put a fudge factor. The Instructions tell you to put negative 4.1. In reality, I think negative 3.6 is a better fit for that because this is like 3.6 inches below my actual zero. So that's called a suppressed zero. Because if I didn't leave this alone, it wouldn't accurately measure the size of that tank correctly. Head pressure, these are all pretty good. Head pressure would just be that, like whatever the pressure is pushing on your input side of something. My first highlight on 8 and 9 is on 213, Principles of Operation. The first sentence, a pneumatic differential pressure transmitter has a two-sided differential pressure capsule that receives two different levels of pressure and converts the difference between the pressure into a mechanical movement via a force bar. I underlined converts the difference and like wrote out to the side subtracts. So all it does is subtracts the difference. You're taking your head pressure minus your zero and figuring out what your difference is. This is like the inside of the differential pressure meter. To be honest, I don't talk about this a whole lot. I haven't studied this a whole lot because if the inside of this goes bad and like the force bar gets messed up or something like that, you're replacing this. You're not going inside of this and messing with the feedback bellows or anything like that. You're replacing this. So I don't go into this a ton. Like the insides of how it works. Like you can read through and see how stuff works, and literally it's just like levers and pressure and stuff like that, and moving stuff around. But for the purposes of y'all doing maintenance and stuff like that, it's not. It's good to know how it works, but not super important. But you do have some highlights on how it works. The last paragraph on page 9, first sentence is highlighted. As the flapper partially closes off the nozzle, back pressure is created in the tubing connected to the nozzle, which is connected to the other end to the top side of the diaphragm in a pneumatic relay. Flipping over to page 10 and 11. I don't know that y'all can make it, but I do have a guy coming to talk during the day. I think it's at the end of this month. I think it's like the last Tuesday of this month. He's going to come do a demonstration in here from like 9 to noon. And he's from Rosemount. He's doing it for y'all's class, but he's going to be very good at explaining how these things work and where they're used and stuff like that. And y'all are welcome to come to that. Just let me know. But I think it's the 30th from 9 to noon. But if you're interested in that, let me know. I know y'all got stuff going on and whatnot, but I think it'll be a pretty good presentation. Page 10, I've got those 3 bullet points in the bottom left, along with the little 2 sentences below it. Notice that the spans of all 3 models have a minimum span limits that are higher than the true 0 point. A minimum span limit above the 0 minimum range is referred to as an elevated 0.
It's like the opposite of a suppressed.
Suppressed.
Yeah.
Page 11. This just talks about other calibration points, which it's just the math. I have the first paragraph on page 11 highlighted. For other calibration points, determine the actual range of the span and figure the differential pressure at each of those points. The range of the span for 5 to 50 inches of water is 45 inches of water. 5 minus 50 is 45. For the 20 to 255 is 2. I'm not going to do all that, but you're just to find the span. You're just subtracting the range. Got to know how to do that. Page 12, pneumatic calibration process overview 214. Step 1 is highlighted on page 12. Step 1 is isolate the transmitter from the process by coordinating the isolation process with the proper operations personnel. This usually involves operating a loop and controller in the manual position. Never, ever, 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 ever take something out of service without telling your operator. It's a bad day. Like, they're going to see something on their screen go to 0 and they're going to freak out. Never do anything without talking to your operators. It's a good way of getting operators to not like you. Always go talk to your operator first. Should be obvious. You can read through the steps of that if you want to. I don't have anything else highlighted. 215 temperature transmitters. Second paragraph. Is that only the second sentence? Second paragraph, second sentence of 215. A bench calibration check can be performed on a bulb type instrument by providing a calibrated temperature control bath in which the bulb is inserted to simulate the process while monitoring the pneumatic output of the signal using a multifunction calibrator. Temperature is used in a ton of different places.
I seen that, I was wondering what that was.
So this is a dry well calibrator. So we've talked about, you guys might not have yet, but why am I spacing on the name? Thermocouple goes in a, where does the thermocouple go inside of that protects it from the process? What's that called? Thermowell. Thermowell. So you have thermowells that are different sizes, right? So this has a little sleeve, and they have different size holes for different size thermowells. So literally, you just pull your temperature or your probe out of there, stick it in this thing, turn this on, and you can set it to a very, very specific temperature. Right? Like this is very, very accurate. Any guesses on how much that is?
10,000.
5,000. It took months to get. Huh? Just to get an exact temperature. I'm gonna try to like set up a lab this semester for y'all to mess with that. But we'll see. Like that'll be an extra thing. Like that's not something y'all are already doing it on the other trainer, but I'd like to use that as well. They bought that because they're trying to get the methanol plant back there to operate in automatic mode, and they needed one. But they're saying you can do like instead of, so say they're working on something out there and they can set like a temperature to what it's supposed to be. Say they're not confident on their temperature settings. They can pull the thermocouple out in the thermowell, take it into the lab, and you can do a bench calibration where you set it to the temperature you think it's supposed to be, and then you grab a process meter or something and you see whatever the output's going to be, like whether it's milliamps or whatever. You make sure that is tracking correctly with what it's supposed to be as far as temperature. Analog multifunction calibrators 221. The whole second paragraph's highlighted. This calibrator can also provide an auto step or auto ramp source in which the source function can be automatically set to provide a complete range or span in incremental steps, such as 4, 8, 12, 16, and 20 milliamps. It may also be programmed to provide automatic step source pressure head of any range or span. This feature allows the technician to set the calibrator for auto step or auto ramp as an input at one location and check or test other parameters at different location as the calibrator steps through the various levels of the source. This is nice when you're working by yourself. You can set this thing up and it'll do 0%, 25%, 50%, 75%, 100%. And you can, because not always the thing you're working on is here and here. Like a lot of times, like in plants and stuff, you're working on something here, and then you have to go to the control room flipping 100 yards away to go calibrate it. So either you gotta have a partner with radios, or you can actually set up one of these to do a step function. You can go in there and say, like, for some reason the 50% point is like 10 degrees off or something like that. Like it'll step through those for you. Like you just push a button and it'll start doing the different steps. Head pressure 223. First sentence of 223 is first sentence of 223 is highlighted. Differential pressure transmitters used for liquid level applications measure static pressure, commonly called head pressure.
Is that what that is?
The pressure meter, yes. Yeah. But that's also what the one you're going to do in the lab is. I mean, that's why I talked about head pressure is pushing onto your high side of your transmitter. Open vessel installations for level measurement. So this will be literally like what you're going to do in the lab. That's open vessel, so that means it has an open top, open atmosphere is what it means. Second paragraph, first sentence. So last paragraph on page 13. If the transmitter is mounted below the physical minimum point of the desired level range of the tank, a zero suppression calibration must be performed. Next page. I don't have any of the math for calculating the range. The range of stuff, you can go through that if you want, but I don't have any highlights at all on page 14. 225, closed pressurized vessel installations for level measurement. Well, that's like what I talked about on the board, 225. My first highlights on the right-hand side of page 15, the first full paragraph, first two sentences. Low side transmitter piping in a closed pressurized vessel installation will remain empty as long as the gas above the liquid does not condense. This is referred to as dry leg installation, which is what I talked about earlier. I always should have waited for it. The immediate next paragraph, the first three sentences are highlighted. However, if the gas is in a closed pressurized vessel condenses, the condensation will eventually fill the low side piping or tubing. To address this issue, the low side tubing or piping is purposely filled with convenient reference fluid. This filled pipe is known as the wet leg. Did I go with that? Moving on. They do more of the span calculations. I don't have any of those highlighted. 226, Rosemount zero and span. Brandon, this should look fairly familiar to you.
With the plate.
Got the little plate that you swing that's always out of the way. You will do a zero and span calibration on that 5552 trainer. But they go through the steps on that and how you swing the plate out. Then there's two little buttons. And because they put ours so close to the thing, you got to take like an Allen wrench to push it all the way down. But you go, like, you can read through the steps, but you're going to do that 3 separate times in the last lab that you do for that trainer. I mean, it's easy because you're following step by step, but it's not. It's 2 buttons. Like 18, page 18, 227. Temperature transmitters with analog outputs. Third paragraph, first sentence is highlighted. The 2 most common types of temperature sensing devices connected to a temperature transmitter are thermocouples and resistance temperature detectors, RTDs. That should sound familiar. RTDs and thermocouples, those are going to be your most common ways of sensing temperature. Next paragraph, the whole thing's highlighted. I think it's only 2 sentences. A good calibrator Offers several temperature-related functions, including thermocouple identification and simulation. This second feature is especially handy when calibrating temperature transmitters. I underline simulation. So a good calibrator has the simulation. So that that's like the doing the 0, 25, 50%, 75%, 100%. So a good temperature transmitter or calibrator will do a simulation of temperature. You got the section review number 2 on page 19, but again, I'm just going to continue on to page 20. Sorry, I know I keep going and getting stuff, but there's something else I want to get. Smart transmitters. You probably have heard of HART communication. I don't ever remember. It says highway addressable remote transducer. This is just ways of talking to different transmitter controllers. So you can talk to most transmitters through HART communication, no matter what the brand is. It's just a way of communicating over a 4 to 20 milliamp signal. Very, very useful. A lot of stuff is HART compatible. My first highlight is in the first paragraph on page 20, the sentence that has the factory characterization highlighted in it. The factory process, underline factory process. The factory process for generating the sensor performance profile is called factory characterization. If you ever see where you can change that in one of your meters or something, do not touch that. That will throw your meter off indefinitely. Like, that is done at the factory. Do not change the factory characterization. HART protocol 310, what I was just talking about. The third paragraph, first sentence is highlighted. The HART protocol provides a two-way digital communications compatible with the industry standard 4 to 20 milliamp analog signaling, analog, used by traditional instrumentation equipment. You should know a 4 to 20 milliamp signal is analog or digital? Analog, because it can go from 4 to 20. What's a digital signal? It goes from what?
0 to 120.
What?
0.
So 2, 0, 1. Digital is just going to be zeros or binary, right? Whenever I say digital signal, I want you to think binary, discrete, ones and zeros. When I say analog, think of like variance. Like you can have a variance. A lot of, like I've said to y'all before, a lot of people say analog like it's old. Analog does not mean old. Analog just means a varying of change. They have smart communicators. So this HART 475, that was the standard for decades. That's what I used when I was in a plant, everything like that. The new thing is it's called the Trex unit.
Like a computer vision thing, like a car scanner, yeah.
Like it looks like a car scanner, like pulling this thing all the way out. Like you have the cable that can connect to each of your devices with little alligator clips on them.
We have some of those. I don't know what we use them for.
But it's pretty much just like a little computer, stuff like that.
Nice.
$13,000.
Yep. We have 2 of those. One of them is like big. I have no clue what we use it for.
Talking different stuff. I'm trying to get to use these out in the methanol plant with y'all, but I'm waiting on them for some stuff because, like I said, I'm not doing anything else. I'm not working on that methanol plant.
Methanol plant sounds fun.
It would, if I was not doing as much as I would, I'd be out there messing around with it.
Right.
But it's too much. they have to redo, like they're above my head with redoing the PLC stuff out there. Like they had to change from, I can't remember what it was. They changed to Allen Bradley.
From Siemens?
I don't think it wasn't Siemens.
Mitsubishi? Probably. Unless it was like some cheap stuff.
I haven't been over there since like 2017, so I don't know.
Well, I probably haven't run an automatic since then either. But, alright. Page 21, 321, Heart Device Internal Stage Summary. So you can see, like this is your different stages. Your input stage, so this would be what comes in. Your input, obviously your input stage. Conversion stage, this is what does the math. And then output stage, that's what it's been converted into. And then your calibration is done either on your input or your output stage. You never ever, like your factory characterization is what happens in the middle stage, and that's what you never want to change. You don't want to change how this thing does the math and calculations and stuff like that in order to make an output. Yeah, calibration involves the first and third sections, never the second one. Top right of page 21, the last sentence of that started paragraph in the top right. Conversion of the analog process signal to a corresponding digital equivalent prior to being sent to the first stage is done by an analog to digital converter, ADC, in the processor. Page 22. Last two sentences before 322 are highlighted. In this stage, the internal calibration factors are used to obtain the correct output signal values. 4 milliamps response to 0%, 20 milliamps response to 100%. Adjustment of these factors is commonly called current loop trim. Key in on that current loop trim. So you read about the input stage, nothing highlighted in there. The middle stage, 323, I've got the first two sentences highlighted. When both the input and output stages of a heart device are calibrated, it should operate correctly. No calibration is required for the second stage because it only performs calculations. The output stage, last paragraph of that, the whole thing's highlighted, top right of the page. If the test fails, the output stage should be adjusted following the manufacturer's procedure for trimming the stage. The manufacturer may call this procedure current loop trim, digital analog trim, or 4 to 20 milliamp trim in its service literature. Adjustment involves two trim points close to or just outside the 4 and 20 milliamp. Page 23, 326. Test and calibration considerations. This is just factors taken into consideration when calibrating heart devices. I've got the first sentence of dampening highlighted, or damping. Damping. Some heart devices support a damping parameter that causes a delay between the change in the device input and the detection of the change for the output from the device. Why would you want to do this? Why would you want a delay from whenever you have your three different sections, like you have your input side, middle side, output side,
Make a calibration.
and necessarily calibration
Stabilize it.
to make it more stable.
Right.
Because if you changed it immediately, as soon as it goes up, like it's gonna, the output stage is gonna do this. Dampening is gonna let you have a little bit smoother curves and stuff like that. Skip a sentence, and I've got the next two sentences highlighted. Settling time is the time to test or calibration process waits between sending the input to the device and reading the resulting output. For this reason, the device dampening value should always be set to 0 before performing any test or adjustment. Digital range change. I've got the last sentence of that bullet point highlighted. So all the way at the bottom left of 23. Calibration always requires a traceable external device. such as a multifunction calibrator to supply and monitor an input signal to the device under calibration. They go through the zero and span adjustment, loop current adjustment. I don't have anything in those. That's all my highlights for section 3. But good. Going on to our last section. Transducers and control valve positioners. 410, transducer. First sentence is highlighted. The function of a transducer is to receive a linear signal in one energy form and convert it into a linear signal in another energy form. So, what's the most common type of instrumentation transducer? I to P. Right? Or it is right.
What to pressure?
Huh?
What
I, what does I stand for?
current to pressure?
Current to pressure. So for that control valve on that, I send in a 4 to 20 milliamp signal, and that corresponds to my 3 to 15 psi. So I'm inputting 4 to 20, outputting 3 to 15 psi. Does that make sense? I to P. You have all different kinds. That's by far the most common. You can have voltage to pressure, pressure to voltage, anything like P to I is very common. Like the pressure transducer that's on the bottom of the tank, that's taking a pressure in and outputting a current, right? But I to P, current to pressure, is the most common type. The word transducer literally means to change from one form of energy to another. Last sentence, next paragraph, last sentence, all the way in the bottom left of page 25. Transducers that convert a voltage signal to pneumatic signal are available and referred to as E over P transducers. E stands for voltage. Anybody remember why E stands for voltage?
Wait, what? Sorry.
Why does E stand for voltage?
Electromechanical potential?
Electromotive force.
Or electromotive force?
Voltage is a force, electromotive force. That's why they write it as E. Right hand side of page 25, the second paragraph, the whole thing is highlighted. Figure 17 shows the internal components of an I to P transducer. It is an electropneumatic device that accepts 4 to 20 milliamp signal and converts it to a pneumatic signal. This conversion is accomplished by applying a current to the coil that creates a magnetic field. That's the biggest part to key in on. You're applying current to a coil that creates a magnetic field, which causes a flexible arm to move. Yeah. So you apply a current to this, it makes all of this move, and it lets out in or out more or less air. But like I've said, like you can read through like how these work and stuff like that, but these are, I wouldn't say cheap, but they're a cheap component. You're changing this whole thing out. You're not messing, like obviously like this the bar that moves up and down can get stuck, springs can break, stuff like that. You're never going to take one of these apart and see what happens. Yeah. Control valve positioners, 420. The whole first paragraph is highlighted, and you're going to have 3 questions come out of this. The function of a control valve positioner is to compare the valve stem's position to the input signal and manipulate the actuator so that the position matches the input signal. The positioner is usually connected to the actuator stem by a mechanical link. That half of a sentence is an online test question. The positioner is usually connected to the actuator stem by a mechanical link. Online test question, as shown in figure 18. The position of the mechanical link indicates the stem's position when compared to the incoming signal. If the two don't match, the positioner either increases or decreases the control signal to the valve diaphragm in order to bring the stem to the correct position. Analog positioning. So this would screw, like the big tall valve over there, this would screw to the front of that valve, and then the valve stem in the middle of that would attach to this, right? And as that valve goes up and down, this creates a signal on the inside, like, if it was like something like that, it should be like this valve is 50% open, this valve is all the way open, or this valve is all the way closed. So this is a valve positioner, and if whatever is in the control room input signal doesn't match where it's saying the valve is, this will physically like send either more or less air to the top of that valve to either open or close it. As it open. Page 26 and 27. We're just still going into more like how pneumatic and electro-pneumatic positioners work. Yeah, you can see how they attach to the front. Like inside, I'm not taking the front cover of this off, but the inside, if I take the front cover of this off, like you have this stuff on the inside of that, and this is how you adjust and calibrate the valve positioner. Page 27, the first sentence on page 27 is highlighted. Electro-pneumatic valve positioners are very similar to purely pneumatic positioners, except that a DC current signal is received by an electro-pneumatic signal converter or transducer attached to the positioner. This is just the input to this is pneumatic. So whatever, like the signal coming from the control room is going pneumatic into this, and then they're putting that into the valve. This one is an electro-pneumatic positioner and sends a DC signal into this, and then that converts it into whatever the PSI needs to be for the valve. So you can have different ones of these as well. Page 28. This is a weird highlight. 422, I have the heading highlighted, Smart Positioners Digital Valve Controller, and then out to the side of that, I just wrote another name for Smart Positioners. So a digital valve controller or a Smart Positioner, those are interchangeable. They're just another name for Smart Positioners as a digital valve controller.
Wait, where's that at?
That's the heading of 422.
Oh. And what you put to the side, is it?
I just wrote, like from Smart Positioners to Digital Valve Controller, I wrote an arrow. You just need to know that Smart Positioners, or a Digital Valve Controller, is another name for Smart Positioners. They're interchangeable. Last sentence on page 29 is highlighted. Calibration can be performed in the field using the HART handheld communicator, or may be performed from a control room if the system is integrated with DCS technology. Distributed control system technology. That is all of my highlights. Let me I'm gonna stop the recording.